In this video, we're going to apply Dalton's law of partial pressures to stoichiometry problems involving collecting gases over water. So what we're seeing here is an apparatus that's pretty common in the chemistry lab. We have some potassium chlorate and it's being heated, and when it decomposes, it forms oxygen gas. And that oxygen gas goes up the test tube and down here, and it eventually bubbles up into a container. Now, if this container initially was 100% full of water and then some gas bubbled into it, that gas would actually push out, it would float to the surface, and it would push out some of the water, and that water would essentially come out here and raise up on the sides. But you'd be able to measure the volume of the gas, the oxygen gas that was yielded in the reaction based on if there are any markings on this container. If it went down to, say, this mark right here, you would be able to say, oh, it's however many milliliters of oxygen that was produced. So this is a pretty common way of collecting gas and figuring out its volume in a chemical reaction. Now, let's say that we're given this problem here. A piece of zinc metal reacts with hydrochloric acid, producing 45.0 liters of hydrogen gas. If the hydrogen gas is collected over water at 22 degrees Celsius and a total pressure of 755 millimeters of mercury, how many grams of zinc were consumed in the reaction? Note, vapor pressure of water at 22 Celsius is 19.8 millimeters of mercury. Let's actually, before we get into the calculation, let's actually point out why we're using the term total pressure and why this note on vapor pressure is given here in the problem. So there's a reason for it. If you look at this water here, this water is at equilibrium between liquid and the gaseous phase, as all water will be. And so, because there's going to be some amount of gaseous water over the surface of it, we don't want to include that in our calculations. That would actually lead us to believe that the pressure, whatever pressure we read, is just a little bit too big. It's too high a pressure, and or there's too much volume of gas. That water that's evaporated just inflates our measurements a little bit, but we can correct for that using Dalton's law. So let's go to the problem and the calculation. What we have 45 liters of hydrogen gas. We're trying to find the mass of zinc that was used, and we know that we need to go from liters of hydrogen to moles, and then moles of hydrogen to moles of zinc, and then we can get to grams of zinc. And to do that, moles to grams, we use molar mass. Moles to moles, we use the mole ratio of 1:1. And to get from the liters of hydrogen to the moles of hydrogen, since we are not operating at STP, we do need to use the ideal gas law. So we can say that the total pressure, this is where Dalton's law comes in, is equal to the pressure that the hydrogen gas exerts plus the pressure that the water exerts. That's important because we only care about the hydrogen gas. And so from here, we can get to 755 millimeters of mercury. That total pressure is equal to the pressure of the hydrogen plus 19.8 millimeters of mercury being the vapor pressure. If I subtract out the vapor pressure, I get to 735.2 millimeters of mercury. And that is the pressure being exerted by the hydrogen gas, which is what we're interested in. So from here, we can say that there's PV equals nRT. The number of moles of hydrogen, that N, is equal to the pressure exerted by the hydrogen times the volume of gas, which is 45 liters, divided by the gas constant times the temperature, which is 22 Celsius. 22 plus 273, we're going to have 295 Kelvin. Whoops, that should be there. 295 Kelvin as our temperature. All right. So there we go. And if we calculate it out, what we find is that we have 1.80 moles of zinc. And from here, we can just do dimensional analysis, right? We're at the point of 1.80 moles. We've done all the gas law stuff, the Dalton's law, the ideal gas law. Now we're at straight up classic stoichiometry. So we just say 1.80 moles of hydrogen. We multiply by the mole ratio of zinc to hydrogen. Whoops, it's going to be this. We then get to multiply by the molar mass of zinc. And from here, we find that there are, 120 grams of zinc with the correct number of sig figs, since we were limited by the 22 degrees Celsius here. So it's going to be 120 grams of zinc. And that is how you use Dalton's law of partial pressures in a problem where you're doing gas stoichiometry involving collecting gas over water. So I hope this video has been helpful. Feel free to leave any questions or comments in the comment section below. Thanks for watching.